Hi guys, for this week's lecture I'll be guiding you on how heat transfer works, specifically on basic concepts of heat transfer. Why do you even bother to learn about heat transfer? So heat transfer is to predict the energy transfer between material bodies. Science of heat transfer explains how heat energy may be transferred, predict the rate at which the exchange will take place, the difference between thermodynamics and heat transfer. So thermodynamics deals with system in equilibrium. It may be used to predict the energy required to change a system from one equilibrium state to another, but it doesn't predict how fast a change will take place. So we'll be looking at the difference between thermodynamics and heat transfer. Alright, so consider the cooling of a hot steel bar which is placed in a pail of water. Thermodynamics may be used to predict the final equilibrium temperature of steel bar water combination. Thermodynamics will not tell how long to reach the equilibrium or what the temperature of steel bar after certain length of time. So this is the difference between heat transfer and thermodynamics. Heat transfer is a study which predicts the energy transfer which takes place between material bodies. It is due to the temperature difference. Heat transfer explains how heat energy may be transferred. It also predicts the rate at which the exchange will take place. Thermodynamics, on the other hand, deals with systems in equilibrium. Thermodynamics may be used to predict the amount of energy required to change a system from one equilibrium state to another. Thermodynamics may not be used to predict how fast the change will take place, since the system is not in equilibrium during the process. Do not confuse or interchange the meanings of thermal energy, temperature, and heat transfer. Thermal energy is energy associated with microscopic behavior of matter. The symbol used is capital letter U, and the units used is in joules or joules per kilogram. For the temperature, it's a means of indirectly assessing the amount of thermal energy stored in matter. The symbol used is capital letter T. The units used is in Kelvin or degree Celsius. Heat is the amount of thermal energy transferred over a time interval. The symbol used is capital letter Q with the units joules. Heat rate is thermal energy transfer per unit time. The symbol is small letter q with a unit in watts. Heat flux is thermal energy transfer per unit time in surface area. The symbol used is small letter q with an apostrophe. Unit used is in watts per meter squared. So this is the units and conversion factors for heat measurement. For thermal energy, symbol capital letter Q is used, units is in joules. Heat transfer rate, the symbol used is small letter q with units in joules per second or watts. Heat flux, using the symbol small letter q with an apostrophe, units used is in watts per meter square. So this is an example of heat transfer, so you understand more when I give you calculation. Alright, so a 10 centimeter diameter copper ball is to be heated from 100 degrees C to an average temperature of 150 degrees C in 30 minutes. Taking the average density and specific heat copper, its temperature range to be is 8,950 kilogram per meter cube and specific heat of 0.395 kilojoules per kilogram degree C respectively. So you have to determine the total amount of heat transfer to the copper ball, the average rate of heat transfer to the copper ball, and the average heat flux. Alright, so the first question you have to find capital letter Q. The second question you have to find small letter q. The third question is you have to find small letter q with an apostrophe. Alright, so to answer all those three questions, you have to use this formula. Alright, so specific heat equals to heat transfer over mass of the copper ball and times it with temperature gradient. The amount of heat transfer to the copper ball is simply the change in its internal energy. Energy transferred to the system is equal to energy increased in the system. So the mass of the copper ball is density times with the volume of the copper ball. Alright? So the density is given in the question. So it's actually 8,950 kilogram per meter cube. The volume of the copper ball is sphere. So the volume is pi over 6 diameter cube. You can either use this formula for the volume, or you can use 4 over 3 pi r cube. Alright, so you insert the value into the formula and you will get 4.686 kilograms for the mass of the copper ball. Once you did that, you insert all the value that is given. So this is the specific heat given in the question. The temperature gradient is given in the question. So you insert all the value into the formula, you will get the heat transfer of 92.6 kilojoules. Therefore, 92.6 kilojoule of heat needs to be transferred to the copper ball to heat it from 100 degrees C to 150 degrees C. So the second question is, the rate of heat transfer normally changes during a process with time. However, we can determine the average rate of heat transfer by dividing the total amount of heat transfer by the time interval. So therefore, your heat rate is equal to heat transfer divided with the time interval. So the time given is 30 minutes. You change 30 minutes to seconds. You insert the value of heat transfer from the first question. So it's 92.6 kilojoules over 1,800 seconds. Over 1,800 seconds. 800,000. So then you will get 51.4 watts for the heat rate. Alright? So for the third question, heat flux is defined as the heat transfer per unit time per unit area, or the rate of heat transfer per unit area. Therefore, the average heat flux is heat rate over the area of the copper ball. So the area of the sphere of the copper ball is pi d squared. Right? So you insert all the values and you will get 1,636 watt per meter squared. Alright, next we'll be looking at conduction. So there are three modes of heat transfer. We've discussed it before, last week lecture. So there's three of them. There's conduction, convection and radiation. But I'll focusing only on conduction. Alright, only on conduction. Okay? So conduction of heat transfer. Conduction of heat transfer is energy transfer from high temperature region to low temperature region. We said that the energy is transferred by conduction. it used concepts of atomic and molecular activity. So in solids, atoms are bound to each other by a series of bonds analogous to springs. Right? So the first image you can see here, this is a network of atoms. So the particles from hot side migrates to the cold side. Right? So then the hot side will vibrate. So what happens is the hot particles collide with the cold particles, and then when it starts to collide to each other, the whole structure starts to vibrate. So then these two particles have similar energy levels, and both are warm. So in fluids, conduction occurs through collision by the freely moving molecules. So from high temperature, initial temperature, to low temperature. And the heat transfer rate per unit area is proportional to the temperature gradient, where heat rate is in watts, so the unit is in watts, with the heat flux. So heat flux is heat rate over the area of the substance. The unit is watt per meter squared. The symbol is small letter q with an apostrophe, and the temperature gradient. Alright, when proportionality constant is inserted, so when the K constant is inserted, so K constant is the thermal conductivity of the material or the substance. Alright, when the minus sign is inserted, it means it's actually it's inserted so that the second principle of thermodynamics will be satisfied. So the second principle of thermodynamics is the heat must flow downhill on the temperature scale. Okay, so this is what it meant. So the temperature goes from high to low. Alright, so then this equation is called Fourier's law of heat conduction. So this is an example of thermal conductivities of some metals. So the K constant of some of the material. Above is defining equation for the thermal conductivity, and K constant has the unit of watts per meter per Celsius degree, which the heat flow is expressed in watts. Consider the one-dimensional plane wall shown in figure above. If the system in a steady state, example, if the temperature does not change with time, then only integrate and substitute the appropriate values. Initial temperature, T2, the length of the substance, the material, the heat flux. Where temperature at the left face is uniform at initial temperature and the temperature at right face is uniform at T2. If constant K is independent of T, we obtain after integration. So this is the formula for conduction. Right? For the same Q, if the constant K is low, example for an insulator, the gradient temperature over the length of the substance will be large. Example, there will be a large temperature difference across the wall. If constant K is high, example for a conductor, the temperature gradient over the length of the material will be small, or there will be a small temperature difference across the wall. again an example of K constant thermal conductivity of different kinds of material that you can refer to. Alright, you don't worry as much. You should not memorize all of this K constant value. I'll be given, if you have an exam or your test, I'll be given out the value for you to calculate inside your formula. Alright, okay, no worries. Alright, consider a brick wall of thickness of 0.3 meter, which in a cold winter day is exposed to a constant inside temperature. So initial temperature of 20 degrees C and a constant outside temperature T2 equals to minus 20 degrees C. Alright? So the proportionality constant is a transport property known as thermal conductivity. Constant K. Okay? So for the brick wall, constant K is 0.72 watt per meter times Kelvin. So therefore the heat flux is 96 watt per meter squared. Alright? How about if you change the value and then you insert a piece of polyurethane insulating foam of the same dimensions with K constant of 0.026 watt per meter Kelvin? Can you tell me the heat flux is? Alright? If you can. So heat flux, which is the heat transfer rate in the x direction per unit area perpendicular to the direction of transfer. The heat rate through a plane wall of area A is the product of the flux and the area and the area. So heat rate is equals to heat flux times with the area. Alright, please answer this question for your attendance, for your today's attendance. Alright? One face of a copper plate 3 cm thick is maintained at 400 degrees C and the other face is maintained at 100 degrees C. How much heat is transferred through the plate? Given K constant is 370 watt per meter per Kelvin. Okay, so you can use this formula to answer today's attendance. So please answer this question for today's attendance. Alright guys, thank you. See you. We'll definitely see you again. Alright guys, bye.